and gentlemen. Our names are Karina Borovleva and Dasiya Chernitska, and we would like to present our solution of problem number 13, egg white pearls. According to the statement, we should investigate the size of the structures appearing when we eject egg oil or egg white into oil. Let's watch information of egg pearls. As you can see, the beads appear on the jet of egg white, and then they transform into separate drops. At first, let's consider the properties of egg white. Egg white consists of water and proteins. The water and oil are immiscible fluids, so there is surface tension between oil and egg white. In order to measure the surface tension, we used a breathing method, and surface tension was equal about 30 millinewtons per meters. The interfacial tension between egg white and oil explains the shape of egg whites. If pearls are small, surface tension dominates, and we have the shape of balls. After a certain size, the gravity starts to play an important role, and pearls have shape of puddles. Denaturation of egg white visualize the pearls on the bottom of the vessel, and we determined our working range of temperature from 17 to 95 Celsius degrees, because if the temperature was higher, our pearls, water in pearls are boiling. In order to control the parameters of pearls formation experimental setup, we controlled the temperature using stuff connected in auto transformer. We tested the uniformity of ejection and the motion of horizontal tip. You can see in our experimental setup all parameters, and we changed the diameters of 5 nozzles.
Now we can consider the formation of the pearls. Increasing the rate of ejection, we can see that with the increasing of the rate, the mechanism of pearls formation significantly changes. We can see that for slower ejection rate, the related instability occurs, for which the governing parameter is the interfacial tension. And if the rate of ejection is quite big, the bending instability leads to the turbulent breakdown of the pearls, and for this mechanism, the governing parameter is the velocity of the jet. So we can see that we have the competition between the fluid's inertia and the surface tension. So we can consider the Weber's number as the governing dimensionless parameter in this system. So we can see that if we change the velocity of the jet and the nozzle diameter in the big range and make the phase diagram, if the Weber number is really big than critical, we can see the bending instability, but we can see the turbulence only for one set of our parameters. So when Reynolds number is about 20, which is quite uncharacteristic. So we can consider the Rayleigh plateau instability at the main mechanism of pearls formation. The cause of the Rayleigh plateau instability is that the surface energy of the cylinder is bigger than the surface energy of the system of spheres, and we can easily calculate the radius of the pearl from the wavelength of instability from the volume conservation. The Rayleigh plateau instability is characteristic for any pair of immiscible fluids. So here you can see the glycerol and water pearls as like as egg white pearls. The amplitude of perturbation grows exponentially, and we can relate the growth rate of instability and the wavelength of instability growth. And we can see that instability grows on the wavelength corresponding to the maximum growth rate. The possibility of pearls observation is determined is determined by the relation between the growth rate of stability and the characteristic time of observation. If the characteristic time for late return stability is less than characteristic time of observation, we can see the pearls. In other case, we can see the sausage-like structure. Now we can consider the size of the pearls. The simplest model for the inviscid fluid doesn't work for big diameters of jet. That gives the fixed ratio between the pearl diameter and the diameter of the jet, and we can see that that doesn't work for the higher diameters. So we should take into account the viscosity of both fluids, and we can use the Tomatikos model of the two fluids with two arbitrary viscosity ratio. By plotting the dispersion relation for the for the fluids of different viscosities, we can see that if the viscosity of inner fluid is much higher than the viscosity of outer fluid, the wavelength of maximum rate of growth increases. We can calculate the viscosity of eggs by measuring by the following ball viscosimeter, and we can consider the non-Newtonian properties. And we can see that the egg white has significant dependence between the strain rate and the viscosity, and we can consider in our case the growth rate of instability as the shear strain rate. We can find the realizing viscosity in our system by comparing the maximum growth rate for given viscosities and the relation between growth rate and apparent viscosities, which we got for a non-Newtonian liquid from the approximation of experimental data. Please, can I see the time? And now we can see that the bigger is diameter of the jet, the bigger is the apparent viscosity. This is caused by the increasing of the growth rate of instability with the decreasing of the diameter of the jet. So, with the growth of viscosity, the wavelength significantly increases, and you can see that there is the main cause of our experimental results. And you can see that now our theory describes our results quite well. So we can predict that the bigger is the size, or is the diameter of the jet, the bigger is the ratio between the pearl diameter and the diameter of the jet. So the non-Newtonian properties of egg white determine the size of pearls for big diameter of the jet. Now let's consider the size distributions. We can see that there are two groups of pearls, the small ones and the big ones. The small ones are so-called satellites. You can see that they are formed from the breakup of the filament, the thread connecting the pearls. I'll say about it later. And you can see that the subsatellites, as like satellites, are formed. We can plot the distribution for only the satellite drops, and we can see that there are 4 generations of them, which correlates to the recursive mechanism of their formation. And we can write the recurrent relation between their diameters. And now let's consider some features of pearls formation. We can see that it's very common that the pearls are connected with a string. This string is very characteristic for viscoelastic fluids. Viscoelasticity characterizes the elastic characteristics of the liquid. This is caused by the absorption of the protein on the all-water boundary, so the viscoelastic motility appears. And we can see that in our charts, the filaments causes the merging of the beds and the collision of them on the string. So, for higher de Boris numbers, which characterize the viscoelastic properties of the eggs, we can see that the that in the distribution are single drops, the double drops, and so on. And now let's come to our conclusions. The main mechanism of pearl formation is the related to instability. The non-Newtonian properties of egg white increase the size of the pearls. The smaller pearls are satellites and are formed from filament, and the long-living filament connecting the pearls is explained by the viscoelastic motility of absorbed protein on the all-water interface. Thank you for your attention.
I'm Amaury from Team Equal Protecting from France. And I'm going to oppose Team Russia on problem egg white pearls. So first of all, thank you very much for this very complete presentation. So first of all, first, a reminder of the problem. So we study what happens when you inject egg white into hot oil. So it produces pearls, and we want to know how the size of those pearls depends on the temperature of the oil, the ejection and motion speed, the diameter of the nozzle, and the non-Newtonian properties of the egg white. So in the presentation, Team Russia, first of all, reproduced the phenomenon in the IPT website and tried it with different fluids. As for the theoretical approach, they gave us the composition of the egg white and its non-Newtonian properties. They studied the two regimes of decompositions that happen when you pour egg white into hot oil. They managed to find that it was the really plateau instability that drove the formation of those egg white pearls. And from this analysis, they derived the theoretical size of the pearls, which is correlated with the experiments. So now if we look at the better and lesser points of this approach. So first of all, there was a very clear experimental setup with a good precision on the temperature and the speed of the ejection. The theoretical analysis was very thorough, and the graphs overall were easy to follow. However, the problem was only partially answered, because in the statement of the problem, several points were not answered, such as the influence of temperature. We don't know how the size of the pearls depends with the motion speed. We don't have any influence of cooking, for instance. And cooking clearly happens in the video on the IPT website. And we didn't have an influence of the height of oil either, which clearly has an influence. That being said, a whole other part of the problem was answered, such as, for instance, about the several diameters of the nozzles. The influence of viscosity was also studied. There was a separation between different sizes of droplets in the distribution. And we had an analysis on how the non-Newtonian properties and viscoelastic properties of the egg white played a role in the size of the egg pearls. Now, I'd like to ask you a few questions. First of all, about the reproducibility of your experiments, because egg white is not at all a homogeneous fluid, and you had very little errors, so I'd like to ask you something about that. Then you haven't studied the speed of motion, which was a parameter of the problem, so how do you think this actually changes the size of the pearls? How do you think actual cooking is going to influence the maximum size of the instability? And since it's related in one of the key points of the problem, what does changing the temperature of the oil change in the problem? As for the more interesting questions, I'd say, first of all, can we explain this instability you mentioned in really simpler terms, because there were a lot of dispersion relations and big equations, but I think we can understand the problem in a much simpler way. And also, I'd like to come back on what you say about the relative instability, because I really think it's not exactly what's happening here. So, if I may,
sure.
I'm going to start on this really problem. So, in this problem, so if you look, for instance, at the Weber number of this problem, so the Weber problem, the Weber number is the speed squared times the length times the volume of mass over the surface tension.
Yes.
And that's around 10 to the 3 with your speeds. All right? Is it correct? Like the speed are also, so this is around 1 meter per second or a bit less. Rho and the length cancel out, and sigma is around 10 to the minus 3 as you showed in your presentation. Is this correct?
Yes,
all right.
But yes.
For such high Weber numbers, the surface tension plays a minimal role, and relative instability cannot be the main point here. That being said, I think what you observe.
Sorry.
Yeah.
But for example, here you can. But I think that we should consider not the density, but the difference of densities in this reverse number. Yes.
All right. So what would happen if you made the same experiment with colored water in water? with the same densities, would we still observe the instability and
I
curves?
mean that the cold water and water are miscible fluids, and the egg white and oil are miscible fluids, and the relative transibility can occur only for the. I've said it in my presentation. I don't know.
That's true. Right,
and of course, I'm sorry, but you can see such an instability in the water, the relative transibility, in the glycerol, the relative transibility. I don't know how could you explain these videos in other terms than relative transibility.
Yeah, well, then let's do it. That's perfect. Let's do it. So here we don't have a simple fluid. As you said, we have a viscoelastic fluid which has special properties. It's a shear thinning fluid, right?
Yes, shear fluid.
So let's say we have a jet of egg white. No. Sorry, just have some space. So let's say we have a jet of egg white, and we have a small instability in it. So like so. So here we have a bigger radius, right?
Yes.
So and here we have a smaller one. So where is the shear going to be the higher?
The shear is going to be the higher in the thinner part.
Exactly. So here we have a higher shear, and here you have a lower shear. And this is a shear thinning fluid.
Yes.
Right. So here the viscosity is going. So this is the shear.
I'm sorry, but the viscoelasticity and the shear thinning are completely different things. You cannot say that
shear thinning means
is the same as the viscoelasticity. It's completely different phenomena.
Shear thinning means that when you shear it, it becomes less viscous.
Yes, but viscoelasticity means that when you have that your fluids have both the viscous and the elastic fluids,
exactly.
and these are the different things.
Yes, both play a role here.
Both play a role here. Here, of course, I thought about that, but see, for the shear thinning fluid, the structure of the pattern structure doesn't appear.
I think we're spending a lot of time here. Maybe there's other things we can talk about. Maybe the reviewer will want to come back to this.
I disagree with you. I want to.
I think there are other points we can explore. Maybe we come back to it. So, for instance, you stayed in a short range of temperatures, as you said at the beginning.
Yes.
So, what would happen if you went to, for instance, room temperatures or higher temperatures? How do you think that would influence the size of the pulse?
I made my experiment both for room temperatures. I didn't show it in my presentation, but the series of experiments were made, and in our working range of temperatures and in the area of higher temperatures. But for the higher range of temperatures, nothing significantly changes with the size of the pearls, but the reproducibility of the experiments is much less because of the boiling. And in the task was discussed and was seen the denaturation for the characteristic temperatures, as can be seen from the videos from the task, of about 90 degrees.
Well, exactly, but it was asked to study a whole range of temperatures, right? But anyway, you talked about reproducibility, so I think there's also something interesting here, because when I take an egg in my kitchen and I crack it, the egg white is not some kind of homogeneous fluid.
Yes, yes.
So a lot of.
Sorry, you may continue discussion later. Now it's time for technical questions from the reviewer.
So, did you vary the temperature of the egg whites and did any experiments?
With the temperature, yes, I made a series of experiments with changing the temperature of the oil from in our working range and the size of the pearls doesn't significantly changes. The distribution of sizes between the small satellite drops and the big drops slightly changes, but I don't think that it's the very important result. We can talk about this in our discussion.
Was the nozzle diameter varied?
The nozzle diameter was used from the 2.5 millimeter and to the 0.3 millimeters in a diameter. It's the nozzle diameter of the syringe, the 2.5.
So, I'm going to review you the discussion from the Team India. So the summary is that the reporter has done very well in the presentation, and they have explained all the processes which I think was essential to describe the phenomenon. They also explained the experimental setup nicely. They explained the theoretical approach, which was we really liked it. And also they discussed various parameters and showed that how the pearl's shape changes. And the opponent identified also identified certain points which we also thought could be questioned very nicely in order to identify that the pearl size could be varied and could be like the very important question was whether this instability was raylight instability, and other parameters like both of them had a very well discussed arguments regarding, and I wanted to actually make a comment about the Weber number and how that particular number is so critical to identify the stability itself, because the Russia team has described the phenomena using the equations itself, and they have tried to demonstrate and correlate the data. So that was one of the cons of the, that was one of the questions that is left, that why this number is so critical in nature. Next. Okay. So we want to we want to have the discussion on these various points. We think that the temperature of the egg white pearls, of the egg white itself, has an influence over the very formation of the pearls. Well, the oil temperature does make a difference, but the variation of the egg white initially, that can also make a difference, and I want to have a discussion on that part. The changing viscosity of the egg whites means, did you influence the egg white itself with some other ingredients in order to make it less viscous, and see whether those properties can change the size of the pearls?
Thank you very much. You may now start the discussion.
So the first question was the temperature of the egg white pearls initially.
The temperature in our experiments, it began to the bubbles begin to appear in the range of temperatures around 95 Celsius degrees, and with the increasing of the temperature, the rate of their appearance increases. And so for the temperature of around 120 degrees, the boiling spoils all the observation as much, so we don't think that it's very comfortable to investigate this situation.
That being said, actually two influences of the temperature. First of all, as you increase the temperature, the viscosity of the egg white goes down. So in the instability, the significant of size, but also they start to cook, and as they cook, they can't expand anymore. So there is a critical time after which cooking stops what you expect as the relative instability. So yeah, I think that's two factors.
I wanted to confirm whether you were dealing with the temperature of the oil or the egg white itself.
The temperature of the oil on the egg white itself, the denaturation, of course, and also I would like to comment on the changes in viscosity of the oil. Yes, of course, we estimated the changes of viscosity of the oil because of the temperature in our model by the erroneous equation. But in our range of parameters, the changing in the viscosities in such range of parameters doesn't give us the significant difference.
But this is weird, because you said just before that temperature has no significant influence on the size of the egg white, but viscosity decreases from 60 millipascals per second to 5 millipascals per second from like 20 to 100 degrees. We should see a huge difference.
I mean the experiments with the denaturated pearls, and for the denaturated pearls, we make the experiment in our working range of temperatures from 70.
So I just had to clarify something. Did you or did you not observe a change of size of the overall pulse from 20 to 100 degrees? And if so, why isn't this shown?
See, you cannot see the pearls like itself for the 20 degrees because they don't denaturate, you see. Do you agree?
Well, Repeto happens at 20 degrees, right?
Okay, we will go for the next question. The temperature gradient which has been formed during your experimental setup, did it influence the size of the egg pulse altogether?
The temperature gradient in the layer of the oil.
Yes. Yeah.
We investigated this parameter, and we found that for our experimental technique, the difference of temperatures from the highest part, from the top to the bottom of the vessel was about 5 Celsius degrees. We don't think that it can influence.
So did you try influencing the temperature gradient itself in order to see the shape, the change in the egg pulse? Did you have this parameter as in the consideration? It's the question for both of you, if you have it.
No, we didn't. Because it's really hard to control in home setup. No, we didn't.
Okay.
And also regarding the change in the viscosity of the egg whites for both of you, like did you vary the parameters of the egg white itself to change the viscosity, and does that influence the formation of the pearls itself? Did you try to change the viscosity itself of that?
So there are two answers to this. First of all, it's important to note that from one egg to another, the viscosity can change from 1 to the double. So that in itself causes a lot of variability in the experiments. What is more, you can easily add water into the egg white because egg and water are miscible to simply have a linear scale between the viscosity of egg white and water.
We also tried to add water in the egg white, but I think that it changes its properties so much that it isn't very relative to the task.
And regarding the higher harmonics slide, do you both agree on the derivation of the higher harmonics which the presenter has shown?
So can you repeat the question?
Yeah, so can you go to the slide of the higher harmonics?
The slide with the harmonics, please. The 37th, as I remember. Yes.
Yeah, so I was curious to know that how it has been derived. I mean, how this has been correlated nicely with this.
See, on the bottom you have for the higher Dvorak numbers, when the velocity of ejection is quite high, you can see the viscosity which are the pearls which are merged with each other. That's why we have the higher harmonics. This is triple drops, double drops, and here is the surface area. And for the cylindric drops, they have the cylindric form because of the influence of surface tension, because the balance of the surface tension and gravity. That means that the size is really doubled. The volume is also doubled. Do you understand me? Yes? Thank you.
Okay, we have a suggestion to opponent had a very interesting question about the horizontal speed. So could you please turn to this discussion about horizontal speed?
The horizontal.
So you haven't studied that horizontal space. So how do you think it will affect the size of the egg pulse?
I think, of course, the horizontal speed will have an influence if it will be too slight, because the pearls will merge with each other, and we have the structures of such kinds. We have made a series of experiments with this parameter. What do you think about it?
So where is the no graphs about this parameter?
I don't think that it is the most interesting in this task.
Well, actually, if you move very quickly, you have a thinner jet, right?
And we have
so the relative stability scales as the radius.
There, we have the fast growth rate of bending instability, and this leads to the faster growth of turbulence. But in my presentation, I don't think that the turbulence is the most relevant mechanism.
But very clearly, if you move very fast, you have a very thin jet, and so you have very small pearls. According to Plato.
Because of the bending, because of the increasing of bending instability. Yes.
Have you correlated the distribution of the size of your pearls with the various parameters of your thing, so as to make sure that it's Rayleigh's instability that is causing these pearls to occur? Have you varied it? Have you validated your theory that it is the main causing factor is Rayleigh's instability?
Yes. There was a
Can we say it?
Yes, of course.
But in the in the slide with the graph, it was mentioned that it was 5 experiments. What were the changes between these 5 experiments that you have?
We have not the changed experiment, but changed theory.
Okay.
That means I find it a bit hard because in literature.
This experiment we took into account the shear thinning.
Right, but Plato with viscoelastic fluids such as polymers does not have the same wavelengths as Plato with water, for instance. We should find greater wavelengths, and I don't see this anywhere in your graphs. So why is that?
What do you mean? I'm sorry.
So if you do Plato not with water, but with some viscoelastic fluids such as egg white.
It's with egg white.
Yes, exactly. But you took formulas for normal Plato, right?
I do. I modified.
There are no viscoelastic parameters.
I made the modification of the classic theory for the viscose Rayleigh-Platon stability to take into account the non-Newtonian properties of it.
I have a question, please. I would like to know with your theory about Plato as how can you explain then the formation of the bubble we see in the video, since the A is much lower than the one used in your experiments?
Very fast, please.
The formation of the bubbles.
One side.
The video on the IPT side.
Formation of the pearls, not the bubbles, the pearls.
The birds.
Different things.
The formation of the pearls. I'm sorry, could you?
Yeah, my question
Sorry,
is,
we are out of time.
how can you explain the formation of the pearls in the video of the IPT?
We are out of time, sorry. It's finished.
Because of head deflection.
Sorry, finished time. You have 1 minute for concluding remarks.
I would like to thank the opponent and the reviewer for quite interesting and hot discussion. I think that I would like to answer the question because I think it's very relevant. And in the video of IPT side, we can see that the pearls appear because there are initial disturbances caused by the ejection. We can track the motion by hand, and we can see that there are initial instabilities caused by these. And the increase of these instabilities by the Rayleigh-Platon mechanism can be is the cause of the pearls in this case.
Okay. Thank you very much for the presentation. And now we have 6 minutes of questions or curiosities from the jury. Please.
So maybe not a very physical question, but how many eggs in kilograms have you used for your experiments?
Half minutes.
Maybe 10.
10 kilograms?
Maybe, I don't know.
Okay.
There were really most of them, but the most were the syringes because they spoiled very fast.
Okay, thank you.
Okay. Any other questions?
On slide 37, and this is the higher harmonics.
Yes, the high harmonics, please. Sasha, please, high harmonics. 37.
What did you exactly fit on this data?
This is the feeder distribution. The feeded were the standard deviation for the first harmonic, and the feeded was the height of each. The number of counts was feeded, but the mathematical, but the mean. The 1, the 2, and so on wasn't fitted. And here you can see the sum of the Gaussian distributions with the fixed standard deviation and and the mean which increased once, doubled, and so on.
There's a question for the opponent. What is your main argument that this is not a Rayleigh plateau instability?
Right, so very simply, what I wanted to show is that without surface tension, this still occurs by a very simple mechanism. Basically because the part with less radius are more fluid, and the viscoelastic force pulls them back to the less fluid parts. And the Weber numbers goes into that direction.
Sorry, may I comment? We have seen the Rayleigh plateau instability. We're going to see the formation of droplets for the solution of glycerol and water, which doesn't have any viscoelastic or non-Newtonian properties. So we considered this the main cause of the mechanism at the Rayleigh plateau instability. We made a series of experiments.
Yeah, I just had one really quick thing. With Maizena, for instance, which is the opposite of egg white in terms of rheological properties, we have destabilization in this S shape, but no pulse at all.